And with that, I'm going to, for those that are just signing in, please make sure you have selected the language of your preference on the interpretation channel icon on the bottom of your screen. Select English or Spanish, whatever you prefer, and make sure you mute original audio. And with that, I would like to welcome everyone. We're ready to start. Just a couple of minutes to get all the technicalities set up. Welcome again to another Science Talk event of the Permanent Forum of Binational Waters. I want to take the opportunity, as always, to thank our sponsors, Texas Water Resources Institute, Arizona Water Resources Research Center, California Water Resources Institute, Texas Environmental Commission, the North American Bank, or NatBank, as we usually know it. Thank you for all your support to the forum. Today we have a very engaging and busy, very busy science talk, but very worth it. So I'm going to introduce quickly our speakers for today. This is a collaboration effort of two big initiatives, one led by Arizona State University and the other one by Texas A&M University. And you see all the agencies and institutions involved in these two big initiatives. We're going to talk about today's science and stakeholder engagement for water security in the US-Mexico border. So this is two different initiatives, but very, very connected to stakeholder engagement. The first one, we're going to talk about integrating stakeholder perspectives on land use change and water availability in the El Paso Juarez area. It's going to be led by Dr. Saurabh Kumar, and I'm going to introduce him in a bit. And then we have another one, US-Mexico transboundary water along the Colorado River, a risk assessment case study focused on water in the Colorado River Basin, led by Texas A&M University, Dr. Zenon Medina Cetina, who's going to present it, as long as Guillermo Duran Sierra. With that, I'm going to introduce first Dr. Saurabh. This is the first project that we're going to look into today. He is assistant professor at the Arizona State University and part of the Hydro Systems Engineering Group in the School of Sustainable Engineering in the built environment. He's interested in developing methods that integrate disparate data streams to enhance sustainable water management. His current research focuses on developing hybrid models for carbon and water systems, integrating aerial and satellite remote sensing with water system models. He leads the NASA-funded 3-year project that is looking at integrating Earth observations with land use, land cover changes in the transboundary region near El Paso, Texas. And after the presentation of this first initiative, we're going to cover the other one led by Dr. Zenon Medina Cetina. He's associate professor at Texas A&M University. He's an expert on probabilistic risk assessment and management of systems. He received the Tamus College of Engineering Excellence Award for Outstanding Contributions and holds the Zachary Career Professorship II endowment in recognition of his many accomplishments. He's the author of more than 100 research products, including peer-reviewed journal publications, conference papers, government and industry reports, and other scholarly products. His international research diplomacy approach has materialized in the integration of large transdisciplinary teams to formulate models aimed at improving the stability of the regional social, economic, and environmental systems in the Gulf of Mexico, in the Arctic, and across Mexico and US and Canada. Thank you both, Saurabh and Zenon, for being with us today and for sharing all your knowledge. Also, we're going to have Guillermo Duran Sierra. He's a graduate research assistant, Stochastic Geomechanics Laboratory at Texas A&M University. He has 6 years of research experience at what is SGL? Stochastic Geometrics Laboratory, working on site characterization, geospatial analysis, offshore pipeline routing, and probabilistic modeling for risk assessment and management of engineering systems. Subjected to anthropogenic and environmental threats such as COVID-19 pandemic, climate change, and geological processes. He has received the SUT scholarship and has served as president of SUT Tamu student chapter. Thank you, Guillermo. All colleagues, thank you for being here. And with that, I'm gonna share, well, I'm not gonna share the screen, but I'm gonna let you share the screen so you can start. Dr. Saraf, you have the floor.
Thank you, Rosario. Can you guys hear me and see my screen fine?
Thank you.
Thanks for this opportunity. This is an amazing opportunity to chat with folks who think about transboundary problems. And our project is on transboundary and really, although we are focusing on El Paso Juarez area, but many of the, hopefully, you will agree with me eventually when I finish the presentation that a lot of this applies to all transboundary region. So I'll start by thanking NASA LCLUC program. So they have been, they funded this research and we are developing some products out of it, hopefully the community can use. So a quick overview, we're going to do two things. One, first I'm going to quickly introduce the project, the research goals, and some data products that we are developing that might be of use to the community. And then we will follow this up with a short slide of presentation where we want to make it a little bit more interactive. I'm hoping that people will participate and we get some feedback instantly and some ideas and thoughts that can help us out for the project. Raquel, who was not introduced because we decided it later, but Raquel is going to, she's a PhD student at our lab, and she's going to take on that part of interactive work. Let's get into the presentation. All right, so okay, I think I need to start with the team that is working on it. The common thread that connects us is that we all were in El Paso and we are interested in developing things about the transboundary region. So we have three universities working on it: Arizona State, Texas A&M, and Jackson State University. And we have three PhD students, some excellent researchers, and it's really a truly, I hope you will also agree with me eventually that it's a very interdisciplinary project that we are working on. So let's define the study area, and I'm going to call that Middle Rio Grande. I know there are so many definitions for Middle Rio Grande, so let's define this Middle Rio Grande that we are looking at. Essentially, Rio Grande River, all the way from San Marcial, that a little bit above the gauge, above the Elephant Butte Reservoir, if you are familiar with Rio Grande, and then goes all the way down to Presidio. That's really the area that we are calling here Middle Rio Grande. So that's our study area, and it's kind of interesting area. There are over 2 million people in there, in this region, and Rio Grande is a highly managed river. Water only flows, probably like most other arid rivers, only flows when somebody needs it. So it's a very controlled river, highly managed, and most of the surface water, almost close to 85%, has been used for agriculture. The region has two aquifers which are kind of alternate source of water, Hueco Bulsan and Masilla Bulsan. So they also supply a lot of water for agriculture and other purposes in the region. I'm sure there were talks about this in the forum, so I'm not going to repeat everything, but this essentially both are fossil deposits. So there's very little recharge going on in these aquifers. At least that's what the current status is. And also Waco has this salinity issue. So so there are issues with this aquifer, perhaps like every other aquifer on the transboundary region. And then we also there's also urbanization happening in this region, which again probably common to most other transboundary regions, where there's some urbanization happening, which is creating pressure on land use, land cover change. And then there's also an interesting phenomenon of ag intensification. So there, we have found that the agriculture area itself and then the type of crops that are grown are changing and it may not be ideal for given the water situation. So that's something that we're going to discuss a little bit later. As for transboundary aquifers, I think this region has a reasonably good monitoring network. So the triangles that you see is really the flow monitoring network, and there has been a great project which I'm going to keep referring to again and again, led by Dr. Hargrove at University of Texas at El Paso. They did some great work on this, and we are essentially following up on that work. So they did some modeling, and especially for the watershed, they made a model which is crucial for our project. Okay. So, by the way, you will see this again, LCLUC. It's an acronym for land cover land use change, and this is just Lhasa talks a little bit. That's the acronym that they use. So as you can kind of see, like many other arid watershed, again, water is a critical common pool resource here, which constrains land cover land use change. And there are dwindling supplies of water, and I think I covered a little bit. And there's increasing demand at the same time. So there's a demand from cities, there's a demand from agriculture, and ag intensification has to some part to play there. And then there's also demand for environmental services, which is relatively new, I suppose. And then the whole system, I suppose this, I don't have to talk about this to this group, but this system, there's a governance system which is segmented. 2 countries and at least 3 states, New Mexico, Texas, and Chihuahua. So it's not a very uniform governance system either. So the idea that we know there are divergent viewpoints. And again, I apologize for this slide, which looks very different now than it was looking earlier. But anyway, the point that I was trying to make here is that the work from previous work, we know that what stakeholders in the region think are important or is important is actually different. And depending on which sector do you lie in, or which past studies have found quite a bit of difference in what is important and how should it be modeled. So again, this is again a slide from the great work that was done earlier, and so the region has various stakeholders, and we have divided them into, and again, we are following the division that was done by Dr. Hargrove and Heyman in their work earlier. So there's a bunch of stakeholders, and our intention with this project is to reach everybody and try to figure out what is their mental model of the land use land cover change in the future. So that's really what we are trying to get to. So the big science question for this project is how natural and human system interact to influence the land use land cover change when constrained by a critical common pool resource, which is water here. And this I think this question probably applies to all of the arid regions, and especially in the transboundary arid region. But we have chosen to focus on this Middle Rio Grande area. So we also want to see what the future land use will look like for this region, and develop models for it. And then using the different mental models of people. So what are mental models? So I'm going to talk a little bit about this mental models in a bit. So let's just hang on to mental models. And then we also want to develop a digital twin of sorts for the region, so that we can understand if interventions are made, how land use, land cover may change. So that's the big picture questions that we are trying to tackle with this project. The project plan, and this is a detailed plan on the top right, but essentially is simple. We want to quantify the current land use, land cover change, identify the drivers, and then figure out, and then create a methodology to look at a diverse viewpoints from various stakeholder levels that we discussed earlier, and then use that understanding to project the future for the region. And in the process, we want to create a framework which can be applied more regionally, and perhaps to all areas in the transboundary region. So the land use, land cover change that has happened in this area, and it is not very clearly quantified. There is some work which has been done, and the figure on the left is from this paper in 2018 by Dr. Mubako et al. And they looked at the same region essentially, and they looked at how the area, the overall area for different land use types has been changing. And as you can imagine, they found that the urban area is increasing, and so is, for some reason, after 2010, a sudden increase in the agricultural area. And so essentially, you're looking at the green plot here. So, but we didn't really get to what types of agriculture is changing and where exactly is it changing. So are we getting more pecan, or are we reducing cotton and things like that? So the first step that what we are doing on, and this, we have created a data product for it, and I'm going to, okay, this is quite a bit happening on this. Essentially, the first step that we want to do is create a data product which has land use, land cover change for the region for past decade or two. So we tried several models, and it's amazing what AI can do these days. And we have tried several different models, and one of these models was MANet, and it performed really well. So I would like to draw your attention to this confusion matrix here. I'm hoping that you can see my plot. So we were very interested in alfalfa, cotton, pecan. They are three main crops in the region, and we were interested in them. So we have been able to predict quite accurately each of these classes. And if you think about it, the places that we are not predicting is essentially 5 and 6, which is forest shrubland and barren grassland, which are very similar. And we are still working on improving this model. So one of the first data set that we have created, and it's available, is it's the land use, land cover for, right now we have 2023 posted online, but it's available, and I encourage everybody to go and browse this. And although our metrics look very good, but it would be nice to get some eyeball tests and see if it's really what it should be. And our plan is to create this data set, not just for 2023, but all the way from early 2000 to 2023. And hopefully, if the models work well, we can potentially extend this to other areas, the similar areas, especially in the transboundary region, is something that we want to work on. So that's the data set. That's essentially what we have, is how land use, land coverage has changed in the past. Right? Now, the next part of the thing that we wanted to go for is try to understand how would things look like in the future. And this, I'm getting back to mental model and trying to figure out how different stakeholders' mental models, with different stakeholder mental model, what the future may look like. So I said I'll talk about mental models later, but essentially mental models are a framework or way of thinking that stakeholders have that will impact their decision making, and that eventually impacts the land use change. So we are trying to understand what is their model when they're making changes like intensifying agriculture or something else that they think will happen. So that's our idea, and I have one kind of a toy model up there. So what do you when you say think about land use, land cover change, what are the things that you are considering in your mind? And we want to capture this idea. So we have some time series data for past, and then we want to convert that to the mental model, and that's really one of the research that we have been doing is trying to create this software where we can, we can approach people and ask them to create a graphical network essentially, and try to say if, for example, in this case, what factors are changing the pecan area in your perspective. And once they can create the factors, one of the hard part is really quantifying the strength of relationships. How does one factor affect, how strong is it? Is it a positive or a negative relationships? So the key innovation here is instead of asking our stakeholders to quantify this relationship, what we want is to predict the stakeholders to look at the past data and predict the future, what they think the trends of the parameters that affect that main parameter, target, like pecan area is the main target. So how is surface water availability going to change in the future? And we are going to learn the strength of connections from there. So essentially, if you're a stakeholder, you can and you agree to participate in the study, what we're going to ask you to do is create this model, and this can be any model. We have some past data which is already populated, and we're going to ask our stakeholders to change the graphs to see what the past looked like. If you think that, hey, we didn't do a good job, maybe the past was different, you can change the past. And we ask you to generate the future. What do you think the future looks like? We just plot it by plotting it on the graph based on the trends maybe you have seen in the past, or based on what you think is going to happen to some of the quantities that are important. And then what the system does is really based on your input, is tries to create connections and tries to create the strengths of connection. And again, this is not a one-time thing. You can keep doing this. And once we have this, it will help you create a mental model of the system, of at least what we are calling is your mental model for the land use, land cover change in the system. And the questions that we are posing is, how is pecan area changing? How is cotton area changing? And some of the urban areas are changing. So we are hoping that this will help us figure out, the key thing that it will help us figure out is how the mental model of different stakeholders differ. What are the do perhaps growers think that the pecan area is going to increase or is going to stay same, or do they think that salinity is a big driver of what happens in the future? So those are the kind of questions that we want to get to. We want to look at how the mental models are similar and different groups, and how they are divergent between different groups. That's really one of the key questions. So this is really still very early on the project, and there are lots of stuff that we want to do. Right now, we are concentrating on creating the past data sets and developing this mental model and testing it with a small group of people. I'm hoping that some of those would be from this community, and we can get some active participation from the community here. So again, last to come, I said, I think I have covered most of this. How are we doing in terms of time? I think we should be okay. So I think to make this a little more interactive and also get some idea feedback from the audience, we have created a few questions. And we need some interaction from you. And I'm hoping that you can help us out and we'll see. Well, let's see how it goes now. Raquel, so to get this going, you'll have to join us on this slido.com and put on this number. Slide. I'll give everybody a minute to get on. So one of the first questions, Raquel, do you want to go take this on now?
Yeah, sure. Hi, everyone. I am Raquel Neri. I am the PhD student working in this project. And so we are interested in what you think about the following questions. Our first question is, in the last 20 years, how has the agricultural area in the transboundary region changed according to your perspective? We have also the translation in Spanish. I don't know, Rosario, if it's needed if I read it in Spanish or if this is being done in the Spanish channel.
It is done in the Spanish channel, and they can read it. I mean, for the Spanish speaker, they can read it and they can hear it too.
Okay.
And this is kind of very interesting because agriculture area is depending on where you are. I suppose it has increased or decreased depending on which region you are in last 20 years. And you expect from an outsider's perspective that all the issues that we had with droughts and in the region, that we will have a decreasing agriculture, but that's not necessarily what has happened.
Okay. We can move to the next one. What do you think?
Yeah. So
how many answers do you have? Are you able to see how many answers you have? Is everybody comfortable with the QR code? You can just put your cell phone in the screen and it will pop up automatically.
If you're on a computer, you can do slido.com and enter this number. That should also work.
Okay.
I think really the third question is so I suppose people are convincing around that it will increase, I would have thought that it will decrease, but yeah, it's kind of interesting how people have different perspectives. And
this is the second one, right? Okay.
this is the second one, yes. So now we are thinking about next 20 years, what will happen. So we talked about the past and in next 20 years. And Raquel, do you want, should we go next one?
Yeah. So the next one, we want to know what are the drivers that you think are the factors causing these changes in agricultural area land use. So this is an open question. You can put any type of factor you might think of.
How long do you want it to be? Do you want just, or do you don't want to say anything? You just want the mental model to drive by itself?
So I think one of the key things, I suppose we should mention why are we doing this. So I think this question is really helpful for us because it helps us identify systems, maybe things that we haven't thought about, and maybe critical for the region and for analyzing how the land use land cover change will happen, and how will things change. And like globalization is a nice example of that thing. So maybe we can give a couple of minutes for people to key in their answers and stuff. So water, urban area are becoming key things here. Oh, I'm sorry. Did I move forward? So at the end, we're going to give you an opportunity to build on this. So in the interest of time, if you can go ahead, and we have few more questions. And this is, we were talking about agriculture. Now we're talking about urban areas, and so the question is again very similar. What in past 20 years, what has happened in the urban areas? And I suppose everybody will agree here that it has become more urbanized. But I think the more interesting question here is what will happen in the next 20 years? What do people, at least the community, the discussion here as to what do we think will happen in the next 20? So everybody kind of agrees that it's going to increase. That's interesting. Nobody thinks that we're going to go on a decline in a recession or anything like that. Very cool.
You were thinking it was going to decrease?
No, I don't
No?
think so. But I think it may stay constant though. What do you think? It's kind of an interesting problem to think about.
Yeah.
And again, the same pattern. We are trying to figure out what factors do you think it's going to increase? It's just going to be a population migration, or what are the important things that really drive this urban increase? How would climate change play in this thing? Maybe. Migration and nearshoring. Okay, that's very interesting. There's an opportunity. There's some things that I don't understand, so maybe
What is sorrel?
I don't know. I'm sorry.
Oh, it might be sprawl. It's not sprawl.
Oh yeah.
Probably it's misspelled. It's sprawl.
And can you also help me? What is maquiladoras?
Maquiladoras, there's no actually translation in English, but it's basically the industry on the Mexico side
I see.
that has very cheap labor, everything for exporting to the US side.
Yeah, I think so. Perhaps something that we should probably model and look at.
Yeah.
And oh, somebody else is still typing. So essentially, I think in last thing I'm going to ask you for is so we are looking to do this more formally. So essentially, we are looking for volunteers who are from the region, and so that we can help make some people to so we can make a mental model of the system and see how your mental model is compared to other people. And again, you can explore other people's mental model. So we are looking for volunteers if you're interested in being part of study, either directly as a mental model or just you have some comments and everything. Please put in your email IDs, and we will connect with you very soon.
So
Uh,
basically, if there are any volunteers interested in being part of this research, in more in-depth mental model research for this area, please just send your emails on that screen.
and I think we have also created. Oh, I'm sorry. Oh, or you can also email it to me directly. So my email is rather simple. I'll just go back to the screen, but my email is rather simple. Is just SNK and do it ASU.edu. So not terribly hard email to remember, but yeah, that's all we got, and I will be happy to take questions or comments or anything that we had. I cannot see the chat, but
I have the questions.
Oh.
So we have a question from Randall Hanson that says, Saurabh, did you compare your land use methods with the transient invariant cluster method used by Intera for the state of New Mexico?
Oh, we haven't done that yet. So thanks for pointing this out. Maybe we should look at it and see how things are. The only thing that we have compared, so for United States, there is very good land use land cover through crop data layer and other NLCD databases. But I think for Mexican side, there was a little bit less. So what we found the best was a 2018 study, and that's what we have checked with. But thanks for pointing out. We will try to see how that is and look at the data products. I'm wondering if it's both US and Mexico is just United States.
Well, we have another question from Randall that says, did you compare your land use against USGS, LCMAP, CONUS, or against the USGS arrows for SEE land use products?
So we have compared it against mostly against the crop data layer product, which has some of this thing. I think we haven't really compared everything yet. It's very early on. So, but eventually we will probably compare with everything else too. So, but thanks for pointing this out. I'm going to take a note and make sure we do that cover. We do check do that.
I think those are all the questions. We just have one comment. I don't know. We need to read that one out, but the questions, those are all the questions.
Okay. All right. So, and again, if there are any questions or comments that come up later, please do email me. I'll be happy to take those on.
And if there are more questions, if we have time at the end, we can always go back to those comments.
Okay, I'll stop here.
Thank you, Saurabh. Thank you, Raquel, for bringing this interesting approach. And again, if you're interested in being part of this effort, please send your email you can put it even here in the chat. You can email it to Saurabh if you don't mind putting your email in the chat, or Raquel's email. So people interested in participating, please let us know. And with that, I'm going to change it. We're going to go to our next initiative with Dr. Senon. The floor is yours now.
Hi, everybody. Can you guys hear me? Very good.
We can.
So, thank you. So, thank you for the introductions, Raquel, and we're very happy to be presenting here today. This is an evolution of what we've been working in the past couple of decades, but and what we're doing also most recently as part of a project sponsored by the Department of Homeland Security through the Cross-Border Threat Screening and Supply Chain Defense Center, which is a Center of Excellence at Texas A&M University. So I'm gonna ask Guillermo, who is gonna be co-presenting today. He's team lead that has been working in collaboration with Raquel and other experts in producing a model that could define first risk assessment on a particular case study that we're running along the Colorado River. So let's just start. So Guillermo, I think So this is what we're planning to present. I mean, at a higher level, we would like to share a bit about where are we coming from, and then where are we now, and where are we heading to. About where are we coming from, it's the experience that we have accumulated, as I mentioned, in the past couple of decades. But more recently, it's about this particular project sponsored by DHS. And then I would like to finish the presentation with what we're planning for the future and the reason why we're here, because same as the previous team, we would like to call for the attention of potential collaborations in the future. Okay, let's move on. So I just want to start by introducing our team. So all the pictures that you see here are the members of the team that are currently involved in this project that I mentioned, sponsored by DHS through CBTS. Next. This is the team of experts that have been helping us as well across multiple disciplines. And this is what we call our risk task force. And you'll learn a bit more about this in the next slides. So this is basically who we are. So let's talk a bit about where are we coming from. And then Guillermo is going to start by introducing our risk framework.
All right. First of all, thank you very much for the invitation to present. So now I'm going to introduce the risk assessment framework we use in the lab. So we have at the top, and let me use my pointer here. We have at the top what we call the classic definition of risk, or the classical definition of risk, which is risk is equal to hazard times consequences. And these definitions comes since the 1600s. And it has been used for a while in both industry and academia to do risk assessment. Now, in 1979, there was another definition, or an expansion or extension of this definition from the United Nations Disaster Relief Organization, where they introduced the concept of vulnerability of systems, right? And if you see the equation, risk is equal to a hazard, which is a probability of a certain threat. The vulnerability is a probability as well, but it's a conditional probability, and this is the consequence of a system being damaged given the threat intensity. And then you see is basically a function we use to map the impacts of this damage, right? This could be economic losses, could be life losses in terms of social consequences, or also environmental consequences, such as, for example, CO2 emissions or biodiversity loss. Now, in 2008, Medina, Cetina, and Nadim introduced the Bayesian network, or Bayesian risk framework, where you can see that this same equation you have at the bottom is represented in this Bayesian network, what we call the most simplest representation of a model to conduct risk assessment. Something that is important to mention is that in order to conduct risk assessment, we first need to identify the threats, define what are the systems of the study, and then what is going to be the metrics of impact that we're going to measure in a risk assessment. Now, Dr. Medina is going to help us here introducing the two modeling approaches we're using for the projects.
Okay. So to complement what Guillermo mentioned, that risk assessment framework, it's widely accepted across multiple disciplines now. It basically reproduces human decision making. So whenever you hear risk assessment or later risk management, it's because we're trying to understand behaviors and trying to reproduce behaviors. And these three components that Guillermo mentioned are critical for us to define a baseline that we can use to compare if we're improving these behaviors or not. So, and that is applicable to systems, or it can be applicable to social, economic, or environmental systems, as you will see later. Now, in this slide, I wanted to point out that we are focused on developing two, I would say, complementary modeling approaches. On the left-hand side, you see a Bayesian network that follows the same structure that Guillermo introduced before, where you see the blue nodes that represent the threats, that where you see the more brown nodes that represent the systems, and then you see the yellow nodes that represent the impacts, and that will help us to assess the different state of risk of the given systems. So we call this the expert-driven model because similar as the previous theme, so we do expert elicitation by reading all the papers, trying to understand every single report or every single evidence that is available to define the critical processes that define a given state of risk of a given system. So we do that, and this introduces two major benefits. It introduces cost effect, something that is at the core of scientific discovery. We want to understand why things happen. And second is a probabilistic approach. So we can assess what the degree of certainty or uncertainty that our model predictions might have. So in what you see on the left-hand side is produced after having different interaction with experts until we converge to a given model or a favorite model. Then on the right-hand side, we have what we call a data-driven model. And this is what we see now across different applications and disciplines as well, where you use available data to make predictions. Now, the main difference between these two modeling approaches is that if we do data discovery, or if we start about data discovery, we might find only data as we're representing here for T2, C1, and C3 that represent the components that are going to lead us to assess a potential impact within this case, for which we have R1 where we have data. So in other words, we can make predictions from T2, C1, C3 to predict R1 if we do only a data-driven approach. But if we do an expert-driven model, we recognize that there are other processes like T1, like C2, and state of risk that are of interest to experts like R2 that we cannot use if we are only using a data-driven model. So what we're trying to do in our project now is to compare how these two compete and also how can we complement these two approaches with respect to each other. Okay, let's move to the next one. So the ultimate goal of having these approaches is to do regional risk assessment. So I would like to show you some examples of what we have done using this same approach. So we have a group of binational team that have been working in the Gulf of Mexico to identify the critical systems, social, economic, and environmental systems that might have a major impact in the Gulf of Mexico. And through this work, where we have identified processes related to the energy industry, to fisheries, to national security, to transportation, trade. So how are these systems affected by geopolitics or by climate change? And who's going to end up paying if these systems are damaged? So to represent that, we have produced a model that you're going to see in the next slide. So this is the model that follows the same structure that we introduced that Guillermo introduced before, where we have a set of threats, we have a set of systems, and then we have a set of potential impacts that are going to let us assess the state of risk. Now, something, as you can tell from this figure, is we can introduce multiple threats, we can introduce multiple systems, we can introduce multiple impacts, and thanks to the modeling or the expert-driven modeling approach, we can capture that. Okay, let's move to the next. This is another case, a similar approach, same methodology, but this was focused on the Arctic. Same idea, looking at potential Arctic social, economic, and environmental systems, trying to identify their current threats, natural or anthropogenic, and trying to identify the potential impacts. And through a number of rounds by identifying papers, reports, meetings with experts, representing multiple disciplines, we can produce this integrated model that, as I said, accounts for multiple threats, multiple systems, multiple impacts, which are the key elements for us to define a risk assessment baseline that we can use to improve decision-making in the region. Next. This is the corresponding model for the Arctic, just to illustrate the degree of complexity that we can capture when we do this, which follows the same components and elements that we defined before: threats, multiple systems, multiple impacts. Yeah, let's move to the next. So, and this is our most current project, another example. So here the idea was to develop a project that could identify critical supply chains that are relevant for the North American region, from Mexico, US, and Canada. And by working with our sponsor, DHS, we have been able to produce a number of models. And one of these models is a transboundary water model. And we wanted to do risk assessment for that. But in the next slide, yeah, we'll go to the next. So we first, to identify critical supply chains, we first define a major model that could define what would represent the state of risk of any US supply running through its corresponding supply chain. And what we wanted to illustrate here is that the degree of complexity that it can take to account for all processes that can allow for auto parts to be moved from Mexico to Canada, or from semiconductors to be produced in the US and then be sold to Canada, or to bring wood from Canada to the US and Mexico. So all these critical supplies, I mean, we wanted to create first a framework, a grant framework, risk framework model, and that's what you see on the left-hand side. And then on the right-hand side is something we call the minimum viable model, the risk minimum viable model. So we asked the experts what would be the minimum representation of this big model, so that we can implement it and do some preliminary studies on potential state of risk in the North American region. And that's what they produce. But we keep the same components. We need threats, we need the systems of interest, which in this case is the supply chain system that goes from the raw materials all the way to the consumers. And then the different state of risk that we can identify when a supply moves from its production all the way to its selling point. Yeah, let's move to the next one. Okay, now Guillermo is going to talk about how do we do the implementation of this process.
All right, thank you, Dr. Mena. So basically, we created this data management workflow model just to represent the processes that are involved in all, or well, I would say the most recent projects we are working on in all these supply chain models and projects we are working on. So basically, we start with the model formulation and validation. So we formulate a model based on expert feedback, but also reading the literature, validating the connections, right? After that, we go to the data discovery side. So we try to discover data for each one of these nodes or each one of these bubbles using in the model, and we try to inform them with the most complete data set we can find, either from open sources, or sometimes we can get data from private sources, such as Refinitiv, Icon, or other ones, right? And this is just an example of the data we're using for the Colorado River Basin. So this is the water usage for alfalfa hay production. We are focusing our attention on alfalfa hay production. And this is for the different states that are along the Colorado River. We are also working with non-conventional data discovery. And here we are using natural language processing. So we acquire the data from newspapers, and then we process this data, and we can generate some analytics, some maps, or also sentiment analysis to know what is the current state of a given supply chain. Let's say we want to know about the transboundary water, specifically Colorado River between US, Baja California and California. It can give us newspapers and can calculate a sentiment analysis to know what is the state of risk between these two states, as an example. We're also concerned about data management. So we have a protocol we follow to to make sure that the data is properly clean, structured, but also checked in terms of quality control, governance. So our team has established this, I would say this algorithm, but also a kind of a model here where you can see different steps that needs to pass so we can accept this data and we can publish this data in our dashboards or any analytics that we are making it public. Now we're also aware of the archiving issues and how can we archive our data or publications. For example, if we develop technical reports or bulletins, or what we called in the past risk bulletins, which is basically strategic information that can be used for different people. So basically, we use this website that is called OakTrust, where we actually generate DOIs for each one of our research products. And then you can go there and see the citations, you can see all the metadata information, and also access to the big file. Now, in the following slides, we're going to cover what is the data lake operation, the web platform, and development, but also the a little bit of the testing, model testing, calibration. But we're going to start with the infrastructure we are using in order to conduct or to operate all these three big parts of our projects. So here I'm going to ask Dr. Medina to help us with the technology infrastructure.
So what Guillermo basically described is the brains behind the implementation of the model and the interaction with the data to inform the model so that we can make predictions. But of course, it has to be run through a set of infrastructure, physical infrastructure. So we have an ecosystem of servers that we call a data lake. And the data lake aims at optimizing the effort to curate data. So when you have multiple projects that are running simultaneously, and when you have multiple researchers that are covering the same region, you're gonna find out that most of the times they're gonna be using the same data sets or similar data sets, which will lead to unnecessary duplication of efforts and resources. The same happens when you have multiple researchers working in the same region trying to produce algorithms for visualization or for data analysis, and also generating duplication of efforts. So to optimize that, there is this concept of data lake that allows to have the convergence and to expedite production of research products in as part of this ecosystem. So what we have here is something on the left-hand side, you see the physical infrastructure, and on the right-hand side, you see the model that we use to communicate with our stakeholders and the end users of what we're producing. So we have created a model where we have physical servers that are located at the CNN, but we also have a component in the cloud. And that allows us to optimize also accessibility to the data and also produce the highest standards of security that our sponsor requires, so that no harm can be produced by accessing data that is of strict use for a specific set of stakeholders. Yeah, let's move to the next.
All right.
So Guillermo, now, yeah, we'll talk about not the physical component needed to allow this collaboration model to work, but the software component that is needed to run the physical infrastructure. So go ahead, Guillermo.
Okay, thank you, Dr. Medina. Yes, as Dr. Medina mentioned, we are working with DataIQ. Basically, it's a data science platform where you can have different input of data sets, and you can collaborate with other people. So we have two levels of collaboration. One is the explorers, and it's typically the shareholders and stakeholders that get this kind of credential. Basically, an explorer doesn't have the I would say the access to the most technical part of the platform. Is mostly just to explore, for example, the analytics, the results that we are generating without being too technical, right? But the designers, in the other hand, they are in charge of, they can modify, they can run models, they can generate algorithms. And this is basically done by data engineers and data scientists that are part of our team. So basically, they interact with this user interface, and again, DataIQ. And here you can see the models we are working. As an example, we have the Bayesian network modeling here, but also stochastic modeling and machine learning. This is a decision tree, but we are working also with, you name it, like support vector machines and any machine learning, deep learning models that are like the standard now for data science. And then after we produce all the analytics, we produce all the results that we want to show, we move this to our platform. And this is a web-based platform that the project has been sponsoring, where we are basically building all the analytics we want to show to stakeholders, public in general, that they can interact with the maps, they can interact with the analytics, even play with the models so they can see the different results we are publishing.
Okay, so let's move on about where we're standing now. And this is now opening the door for the specific case study we wanted to present today. So this is one of them. So we said we were asked to produce 9 models for critical supplies in the US. And we introduced 2 control variables. One is the complexity of the supply chain, and the other one is the accessibility and relevance of data to inform these models. And we come up with 9 different supplies that are critical for the North American region. And one of them is water. And when we perform our preliminary analysis to identify where this particular supply was located in terms of complexity and evidence, you see that this was classified as a supply of medium complexity compared to the others with low evidence availability. And here in this matrix that you see on the right-hand side, we basically wanted to reproduce the decision-making process of people making decisions about these different supplies. But this was just a sample of them so that others can replicate the process that we're using or partner with us to help them develop their own models and identify the data needed to inform them so that they can make predictions about the state of risk of their corresponding supply chains. Okay, let's move to the next. So these are the 9 corresponding models, just to have a graphical representation, having the same 3 ingredients that we mentioned before, the threats, the systems, and the impacts on each one of these 9 supplies. Let's move to the next. And now Guillermo will talk specifically about the Rio Grande case study that is one of these 9 cases that we're working on in our current project. Go ahead, Guillermo.
Yes, thank you, Dr. Mena. So the case study we defined for this supply chain was actually Colorado River. We chose Colorado River because it's supplying water for 40 million people in 7 different states and 29 federally recognized tribes, and also includes the northern Mexico part, which are Sonora and Baja California. So more than 3 million acres of farmland depends on the Colorado River water, given the geographical location and the arid climate. So it is well known, the droughts and the water scarcity in this region. So they depend a lot on the water supply from the Colorado River. And then we decided to go with more specifically with California. And this is again because we, as Dr. Sanchez always comment on the meetings, the water issues are local. So we need to go local so we can do a better risk assessment. So we decided to go with California because it's the one that takes the most water from the Colorado River. And then we chose one agricultural product, in this case is alfalfa, because based on the estimates, as you can see in the chart, 5.2 million acre feet of applied water are estimated that are used for alfalfa hay production, and this is the most in comparison with all the other agricultural products. Now, the objective of this case study is to develop a risk assessment model for U.S.-Mexico transboundary water supply for the Colorado River, right? And this is just a sample of the model. As you can see, it has around, I think it's around 90 to 100 variables, if I remember well. Now, what you see next is what Dr. Medina presented before in the methodology. So once we define the general or what we call the general model, we go to a minimum viable model, something that we can play with, that we can inform, and then we can study to conduct risk assessment. In the future, we want to come back to that more complex model and run it, but because of the time project limitations, we work with these minimum viable models as a proof of concept, right? So we can run the models and study the results. So something that I want to highlight from this slide is you see the greens and reds. Basically, the green means the data we have discovered. So we have been going through all the open source websites from the Government of Canada, USGS, NOAA, FEMA, and so on. And the red ones represents where we don't have data, right? So as you can see, let me probably zoom in here. I don't know if you can read it, but most of the data we don't have is regarding water prices, labor shortage with respect of the water supply chain, right? The legal framework, financing, information about dam infrastructure or broadband infrastructure. But more importantly, the part of logistics, that's where we are having scarcity of data, such as the water pipe networks, the aqueducts, the diversion canals, data and irrigation districts. And in the set of risk, or the impacts, we have most of the data except in the sustainability of native communities and land degradation. So as you can see, there are some challenges. The good thing about working with this network is that, as Dr. Medina mentioned, we don't depend strictly on data. Also, we can run simulations and see what are the most likely scenarios for these variables where we don't have data. And we can play with that and see how the influence also of adding more information can better can improve the results and better do a job in terms of risk assessment. All right, next we would like to walk through the platform that is right now under development, and I just want to give you the overall idea of the platform that we are building as part of this research project. So I'm gonna stop my slides here, and I'm gonna go to the website. So the website looks like this. Basically, it gives you the information about the project. So what are we working with, etc. And then you have the 9 supply chains that Dr. Medina was showing here, from corn farming to water security to all the way to power or electricity from natural gas. So I'm gonna go to water security. And then the first thing you will see here is the model. This very same model I showed you in the slides is represented here. And basically, if you go to the top, you will see the different types of data we have in this model, right? The data we have discovered. So you have point processes, time series, spatial data, and spatial temporal data. So for the ones that are not familiarized with the spatial temporal term, is basically, if you think about a dynamic map, a map that is changing in time, so that is your spatial temporal. So you have yearly data, let's say, for all the states of the US, and then you can change that in a dynamic map and see the trends as we go through time. So if we go to the filters, you can see that we have the variables classified by each risk component. So we have the threats, or also what we call the drivers of change. And this could be anthropogenic, natural, or also critical infrastructure. The critical infrastructure is basically the foundation of any supply chain. We're talking about bridges, we're talking about broadband infrastructure, dams, drinking water infrastructure, and so on. Systems, we have the water sources, the suppliers, the logistic distribution, the production, the logistic, and also the customers. In our case, we are focusing on agricultural water. So our customers are the farmers or the people that is producing these agricultural products. It could be from alfalfa to corn and others. And then we have the state of risk, and we have 3 main categories here: the social, the economic, and the environmental. So basically, if I filter here by threat, what is going to happen is going to show me only the threats, right? And I'm going to go to population growth just to give you an example of the kind of visualizations that we are developing. So basically, you have your metadata here, and then you have this map. And as I was mentioning, this is a spatial temporal kind of data set, because as you can see, if we move through time, every year is going to have some different values, and it's changing to time. The population, as we know, the population is increasing all the time. So you will see this trend in different states, right? Also, we are generating some what we call the first order statistics, or any exploratory statistics, such as the ECDF or the histogram. So this is just to know more about the data, the frequencies, and so on, the kind of values that you're getting from the whole states in the United States. Now, I would like to give you another example of other data set. This is about, let's see, geopolitics. And as you can see, this is a time series data, right? So this is a little bit different from the dynamic map you saw. Basically, it's giving you an index. This is an index basically that is constructed based on news and different newspapers, and they are collecting this information and generating a risk index, a geopolitical risk index based on the information they are processing. So they have this data since 1985 all the way to 2023. And also you can see their corresponding first order statistics. Another model we have, or tool, is the trend analysis. So basically you can feed a model here. You name it, could be from moving averages to even linear regression. And then what it's gonna do is gonna feed a linear regression model on the data you have, so you can see the trends or whatever analysis you want to conduct here. You can see the residuals and the ECDFs. And also you can play with the parameters. Once you play with the parameters, the model changes. Depending on the type of model you're working with, you can change these parameters, improve your fitting, or whatever model you want to play with to fit the data. Finally, I just want to give you one more example, and this is about profit. And in the case of profit, the ones that are familiarized with agricultural products will know that some of the farmers are not profitable. So it is very hard to find profit as per se, as a data set. So what we found is, for example, the income or the revenue that people is getting for these agricultural products, but also the expenses and different types of expenses. But as you can see, if we see in the different options, you can go from different types of expenses, such as the fuel and oil, labor expenses, and so on. And this is, again, state level data. It's a dynamic map, and you have your corresponding statistics. Yeah, and also I think also that something that I forgot to show you from population growth, just to close with that. We also have data at county level, right? So if we select the state of California, the one that we are interested on, so we can get at county level data for some of the variables where we have available county level data. We can choose, for example, San Bernardino, which is one of the counties that are in our study for the Colorado River, and you can get the corresponding ECDF, the histogram, and also you can check the different years for each one of these counties in California and see how the trends have been changing since 2001. All right, I'm gonna come back to the presentation so Dr. Medina can conclude.
Okay, I think this is our last slide. We just wanted to ask for partnerships. I mean, we built this using taxpayer funding, and all the resources that we have produced, including the physical infrastructure, software, all the work that we have spent in identifying data to fit all the different models. So the concept is to extend this modeling of collaboration, of research collaboration to other groups. And what we would like to hear is interest from this group so that we can define specific projects, specific regions of interest, specific systems that you would like for us to look at, and start new partnerships with you. And I think that's the end of our presentation. Can you set the last one, please? I think we have my contact information on the last slide. There you go.
Thank you. Thank you, Zenon, Guillermo, for the presentation, for the work that you have been doing on this, which is titanic.
Yeah.
And what you have built so far, I think is gonna have a long-term, needs to have a long-term sustainability. So over time. So if the institutions and our colleagues that are from other parts of the states, of the border states and Mexico as well, I mean, it's important that we get to know these platforms in a way that we can, exchange and integrate our efforts together so we can continue on these projects as we move towards the end of some projects, or as the needs grow in the border region. So data is everything. Data in the border is particularly needed, especially in water resources. So we need to get involved in these efforts to make sure that this data is used and it is, usable for decision-making process. So if you have any questions, we have a couple of minutes here for questions. I think I have Saurav is asking a question. Well, Saurav, you have two questions. Do you want to go ahead and just, tell them yourself?
Oh, sure. Well, great presentation. I love this whole infrastructure that you have built. But essentially, it was more like first one was a real question, and second one was more the thoughts on this thing. The first really good question I wanted to ask is, does the infrastructure allow you to do what if type scenarios? I suppose it's the networks are quantified, so you can try to pick things and change, right? And see what happens.
Yes, and that's exactly what we're doing right now.
Okay. Okay.
So these models are mathematical models,
Right.
and if you feed these models with data, you can calibrate the models.
Mhm.
If you calibrate the models, then you can define scenarios for where data was not available, right? That's the general principle of any mathematical model. So, and that's exactly what we're doing now. The only issue there that it's something that we feel really proud about is that there was no methodology to do the calibration of these type of models using real data. And that's a methodology that we're producing. Because it's not the same to calibrate a deterministic model than to calibrate a probabilistic model.
Mhm.
So, and that's something that is coming up. It's in the oven now, and what these models will allow us to do is to run different scenarios. For our particular project now, we're trying to define what will be best case scenarios, worst case scenarios, but we can run any scenario you want to. Of course, if we introduce more data to the model, as we acquire more data, or as more data sets become available, then our confidence in our models is expected to grow. That's one of the beautiful things about working with Bayesian networks and Bayesian inference in general, right? So yes, we can do any scenarios as long as we calibrate the models. Yes.
That's great. Yeah. So I think I'm a big proponent of Bayesian networks, and I think every deterministic model should be converted to a probabilistic model eventually to make it easier for people to use it. I think that's go ahead. You were reacting to it, I suppose.
Yes, and we saw that you guys are working following a similar approach.
Yeah.
So we'll love to talk anytime.
Yeah.
And as I said, our resources are available. and
That's-
the data that we already have produced is available. So what will be great to do is for everybody, once that we release the platform, to see what data sets are available. And if you think you would like us to add more data sets, or if to refine the model for specific applications, that's where I would love to have the interactions and maybe pursue different projects or new projects that that can be based on what we have produced already. So there's no need to collect data that we already have or to produce models that we already have when these are already available.
I think I had the second thing which I wanted to ask you a comment on, but don't want to hog all the time with here. But the quick thing was like I think we struggle with this a lot, that we are developing models and we are even calibrating it. But if eventually it's used for decision making, how do you build trust in people that they are going to use? They're going to use it, and second, if they use it, are you scared that they might reach wrong decision based on your models?
So we developed a methodology to what we call expert elicitation. And this is where we actually met Rosario and other experts, where we first developed a draft of the model based on what is available in the literature. And then we present it to experts, and our experts help us to refine the model. And but what we're basically doing in these two steps is to sample knowledge. We're doing knowledge elicitation. So it might not be perfect, like any other mathematical model, might not be perfect. But when you finish a workshop with a group of different experts that are looking at the interdependencies of critical processes, and they say, we like this model. And when you run simulations without introducing any data, just to test the model, to stretch the boundaries of the model for best case scenario, worst case scenarios, and the model is consistent with what the experts are expecting, then I think you have a very strong argument now to start informing the model, calibrating the model, and then presenting it to those that are going to use it, which is a third step. And this is the reason why we're here. So we would like users to see the benefits of having this approach, which is, as you could tell, is graphical. I mean, you can understand the interdependencies between the critical processes. You can see the data, and pretty soon you will be able to play with a risk scenario generator, where you will be able to play with what will be the best scenario that you would like to use for your specific region, if possible, or for your specific system, if possible.
That's really nice.
We have two more questions. We have a short time, but we do have more questions. Two more, and I'm going to give them quickly to you from Randy. Do you simulate conveyance in the supply chain model, such as ships, planes, trucks, and trains, or just the probability of delivery? And the other one, I'm going to send both. How do you deal with data from Mexico to make your models transboundary?
So let me start with the second question. When you see this graphical model, each node represents a variable. As Guillermo mentioned, it can be a point process, it can be a time series, it can be a map or spatial, or it can be spatial temporal. So if we have data that can inform a model that is a map, we can run this model in a map. And of course, we need to be consistent with the definition of the variables, all being maps, or we can convert that information into probabilities, which is something that we can also do. And when you do that, you're basically sampling or collecting information from a population for a given geographical domain. So, so we have done that actually in the past. We can generate maps after we run our models, so that you can see the state of risk of a given process in space. And we have published a couple of papers on that as well. So we'd love to share the references about that specific question. So that means that if we have the same variables that can cover Mexico, US, or Canada, which is our ultimate goal, or a smaller region, like the case of the Colorado River, yes, we can represent risk maps. And we can see the contribution of each one of the variables, as Guillermo showed in the platform, to the definition of a given state of risk of that particular system, which in this case can be aquifers, or can be the infrastructure to collect water, or it can be social systems, it can be people impacts or communities impacts. So, and we can map them. So this is, I think, something better than just doing a sandwich of maps that can reflect an index. So here we see the interdependencies between these processes in the model, and we can produce risk maps associated to the specific state of impacts that the experts are telling us are critical for them to make decisions. So that's the second question. The first question is about, let me review it again. Could you repeat the first question? I think
Sorry, I was muted. Yes, quickly, do you simulate conveyance in the supply chain model, such as ships, planes, trucks, and trains, or just the probability of delivery?
Yeah, so we can, as I mentioned before, we can work with both. We can work with the actual units of the variables, but we can also, I mean, for something that we're realizing now that we're learning is that the calibration of the models, when they are in terms of probabilities, are simpler. But that's kind of like any calibration process for any mathematical model is a piece of art, right? Where how do you fine tune your model to do that? So so I think we work. You can work with both, and but we're finding that we will work with probabilities is simpler because we can do the calibration of the models based on I mean, we translate the information that we have available for behind each node into probability distributions. And once we do that, then we can do the calibration process much efficiently. Yeah, that's a very good question.
Okay. If you have any more questions, the contact information from both initiatives are in the chat, and we can follow up with that. We are recording this session, so we will share it later in our website and, you know, our social media channels and all that. Please remember that the objective of this is to integrate efforts, to integrate data, and to make it available and usable for decision making. And I think these two initiatives are an example for that. Integrate stakeholders' perspectives and also have them being part of these efforts in a way that they can access the data, they can understand the data, and they can actually visualize the data. It's easier, friendlier, and much more practical, because we need that. We need fast responses, faster every time. So thank you again, Doctors Marina Cetina, and Dr. Saraf Kumar, and all the team, Guillermo, Raquel, for being here today with the forum, all the audience for being here, making the time. But this is worth it, very worth it. So thank you, everyone. Thank you, our translators, of course, our sponsors, and we will have another one pretty soon. Thank you. Gracias a todos.
Gracias.
Mucho gusto. Muchas gracias, Rosario.
Gracias.
Thank you, everyone.